Hi everybody, my name is Mikko Huttunen and I work at the Tampere University and I will be the main responsible person providing you the online lectures for this course on laser physics. So as you may already be aware, this course is organized in a flipped classroom style. So all these lectures are being provided online to you for your individual study. And if we are successful, we are also trying to provide you some podcasting style additional materials to help you deepen your course curriculum, but we are still in the process of starting that task. So we are not sure, do we have time enough already and energy and kind of like knowledge to make that kind of additional material a reality during the few upcoming months. But we will try our best, don't worry. How this course is done in practice is that each week we will be also meeting you in addition to these online individual lectures during group discussions held on campus, and hopefully those discussions will help you reinforcing your learning of the main concepts as well as deepening your understanding of those concepts by going more towards applications. So my personal philosophy on teaching as well as in learning is that I would really like to progress these main concepts side by side by application of those concepts to some real world scenarios, problems and challenges. I believe that this kind of simultaneous approach where we go first introducing the main concepts and then second straight away applying them to some real world issues helps us to really grasp why they are so fundamental and why they are so important. So I hope that you also appreciate this learning philosophy I'm using and you find it useful during the group discussions. But be warned that this approach is a conscious choice. Some people may like it and some people may seriously dislike it, but it's a choice I've made and it's a choice I guess you folks need to just be living with during this course. In addition to the lectures, we will be also providing to you multiple choice quizzes via the course Moodle, so you may or may not use them as you wish, and hopefully they will help you to reinforce your learning. In addition to these, we will ask you to also return weekly homework problem solutions. So those will be regular style calculation based problems that you are asked to solve and return via the course Moodle, and we will then respectively be grading them and they will affect on the overall course grade. At the end of the course, there will of course be an exam. And I just mentioned here that the overall course grading, of course, will not be just affected by the exam performance, but also it will be affected by your attendance to the group discussions as well as your returned homework solutions. More details of the course grading, of course, will be found at the course Moodle page. And then I will actually go and say a few words about the actual curriculum we have at our course. So the course is about lasers. So we really want to understand how lasers behave, how we could build a laser and how we could make a good performance laser. And that's the main point we want to learn during this course. We are using 4 chapters to go through the main points. And the first chapter, called Introductory Concepts, is focusing on the really main points regarding the physics that we need to learn and describe to understand how a laser behaves. So we will be talking a little bit about processes that take place within the light-matter interaction. So we will be talking about spontaneous, stimulated emission and absorption of light into a matter. Then we will talk about the laser idea, so basically how we can have amplification of light taking place in a piece of a material, and then we will be describing about the laser condition and saying a little bit about losses of our laser system and introduce you to a concept of logarithmic losses, which will be extremely helpful concept in what follows, especially in the chapter 4 when we are building a kind of continuous wave laser and want to understand how such lasers behave. We will be talking a little bit also about the pumping schemes, the requirement for having lasers. So essentially we will be speaking about population inversion, and then we will be speaking about different energy level systems that can be used or must be used to understand how a laser behaves. So we will be talking about 2-level energy system, 3-level system, and of course 4-level energy systems in the first chapter. Then in our second chapter about semi-classical theory of light-matter interaction, formidable title, we are talking about semi-classical treatment of light-matter interactions, as the name suggests. So what this actually means, this semi-classical word here, is that we will be describing light fields still classically, so they are still classical fields, no really photons as such, no quantized fields are being treated, and that's the classical part in our light-matter interaction. And then we will be treating the matter part in the interaction, so the gain materials, using quantum mechanics. So essentially we will be solving Schrödinger equation, and we will be describing the light-matter interaction by using a Hamiltonian operator, where we have contributions from the atomic counterpart as well as the interaction with the field. We will be solving this kind of Hamiltonian under the first order solution that gives us a tool to understand how stimulated emission, how absorption and emission takes place under electric dipole approximation. Then we will be speaking about Einstein A and B coefficients that essentially tell us what are the emission and absorption rates of a single atom. And then consequently, we will be introducing to you a Fermi's golden rule as a concept to really quantify what would be the absorption and emission rates of our atomic systems. Then we will be saying a few words about cross-sections of given transitions, and then line broadening as a concept, and then talk about a little bit about mechanisms that give rise to line broadening. So essentially we will be talking about homogeneous broadening mechanisms and inhomogeneous broadening mechanisms, and how these mechanisms affect to the actual line shape of my atomic transition. Then towards the end of chapter 2, I will be speaking about saturation of absorption as well as saturation of a gain, and these processes or phenomena are crucial in understanding how laser behaves. And then we will be speaking about a process known as a spectral hole burning, so basically how saturation of gain affects the behavior of a laser. Then once we are done with the chapter 2, we will be going into the chapter 3, passive optical resonators, and there we really want to understand more how the laser as a device, as a instrument, optical instrument behaves. So we will be first introducing to you a matrix formulation to understand how rays of light propagate inside an optical system. So essentially we will be introducing to you a so-called ABCD matrix formulation that applies under paraxial optical approximation. And then we will be describing a few simple optical instruments or optical components, how they look like under ABCD matrix formulation. Essentially, we will be starting with the free space propagation of light. Then we will be going into thin films, what are their ABCD matrices and mirrors, and then generalize the treatment to optical systems. Then, once we are done with the ABCD formalism introduction of that, we will be introducing to you Fabry-Perot interferometers. And I guess you already are being familiarized or were familiarized with those during the basic optic course, but we will be recapping that material in any case. So we will be talking about a Fabry-Perot interferometer. Essentially, it can be, for example, like a ettalon inside the laser cavity. We will be going through the math, telling what is the transmission function of such an interferometer, and essentially we will go through the main properties, so free spectral range and finesse of such interferometers. So essentially we will be learning the tools how we could control the line width and the kind of like mode purity of our laser by adding a component similar to a Fabry-Perot interferometer inside a cavity. So that's the motivation there. Then later on, we will be talking about optical resonators. So we will be introducing to you the main resonator types that exist. So Fabry-Perot resonator, ring resonator configuration, and concentric resonator configuration. So these are the kind of main resonator types out there. Then we will be applying the ABCD matrix formulation to understand about the stability of our resonator. And there we will be introducing to you so-called cavity G parameters to understand how stable a given laser cavity configuration is. And there I must warn you here already, we are really firmly using the ABCD formulation to understand how to do the calculation, how to do the stability analysis. Then we will be talking a little bit about eigenmodes of an optical resonator in general, and then we will be speaking about transverse modes, Gaussian beam, higher order modes, and so forth to understand that what kind of spatial profiles do we have when we are having an output in our laser, and how the laser resonator configuration affects the output form. And then finally, we will be speaking about photon lifetime, so essentially the cavity Q factor, which tells us about the line width of our laser. So how narrow or broad our laser line is once the laser line is being outputted out of the device. And then finally, in the fourth chapter, we will be unraveling to you how a continuous wave laser behaves. So there we will be first introducing to you the right equations to understand the dynamics. So how the pumping of a gain medium affects the inversion, the population inversion, and how that gives rise to a lasing condition and so forth. We will be combining these differential equations which we have learned in above. So basically the laser parameters, A and B coefficients, cavity lifetime, and so forth. And then finally, we want to understand how a CW laser behaves when a critical inversion threshold is being reached, what is needed, and what happens then afterwards in terms of output power and performance behavior of the laser. Then at the end of the final chapter 4, we will be speaking about multimode oscillations, so both longitudinal multimode operation and transverse multimode operation. We will be speaking about the reasons for multimode oscillation and tell you that what would be needed in principle to realize single mode operation. So we will be speaking again a little bit about processes or phenomena known as a spectral hole burning or spatial hole burning as a kind of means that give rise or phenomena that give rise to multi-mode oscillation. And then finally, we will summarize what we have learned by going through a possibility how we can realize single mode operation inside a laser. So essentially, if you want to minimize the number of longitudinal modes, a quick solution would be to use short cavities. And there, when we need to go into longer cavities for reasons not yet told to you, we will be speaking how we could do spectral frequency filtering, essentially based on those Fabry-Perot interferometers described during chapter 3 to understand how we could kind of adjust the gain profile, the effective gain profile in our lasing medium. And then finally, we will be speaking a few words about spatial mode filtering, so how we could also realize single transverse oscillation operation of our laser. So this is essentially what we will be covering in this course. And all of these different chapters, of course, we have divided them into sub-chapters, and we will have a lecture, online lecture for each of these sub-chapters. So that's the outline for this course. So I will end this first lecture now, this introduction to the actual course, by welcoming you again to this course. This is a very fun course, very fundamental materials are being covered, and this is very practical topic in terms of optics and photonics. So I wish that you will have a fun, pleasant and very educating time at our course. So my thanks and goodbye.